Welcome to a course on classical physics. This is the first video in a comprehensive series where we will explore all the fundamental concepts of classical physics. We will start with the essential building blocks before gradually moving into more complex topics. Along the way, we will break down concepts, provide practical examples, and demonstrate how classical physics helps explain the natural phenomena around us. By the end of this series, you will have a solid grasp of the fundamental ideas that have shaped modern science and engineering. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the first lesson on a course on classical physics. The first thing that rings our mind is that, well, what is physics all about? Now, if you look around your world, you will see that science and engineering are fundamentally built on what are called measurements and comparison. And these measurements and comparisons are to ensure precision. And in order to ensure this precision, we need to establish rules. Rules about how things are measured, how things are compared. And for that, we need experiments to define and validate the units that are used in these measurements. Now, one of the central purposes of physics as well as engineering is to design and conduct these experiments. Now, for instance, physicists develop highly accurate clocks so that time and time intervals can be precisely measured in a precise and right fashion. Now, you might seem that these things might sound very petty, but with these highly accurate clocks, today global positioning satellite or GPS is essential worldwide for navigation, which would not function otherwise effectively. Another example lies in the field of electrical engineering, where precise measurements of voltage, current, and resistance are crucial for the design and operation of circuits. In medical imaging, such as MRI machines, accurate magnetic field measurements are needed to ensure high-quality images for diagnosis. So overall, we can say across many fields from telecommunications to quantum computing, precise measurements are indispensable, making the pursuit of accuracy in science and engineering more than worthwhile. Now, when we talk that precise measurements are indispensable, we need to what is called measure things. How do we do that? Coming up into next part of the video, how do we measure things in physics? Now, we discover physics by learning this, how to measure the quantities involved in physics. And among these quantities, what are very important are length, time, mass, temperature, pressure, and electric current. Now, we measure each physical quantity in its own units by comparison it with a standard unit. As you can see right in the screen, for example, meter is the quantity for length. The standard corresponds to 1.0 unit of the quantity. As you will see that the standard for length, which corresponds to exactly 1.0 m, is what? It is the standard distance traveled by a light in a vacuum during a certain fraction of a second. And we can define unit and its standard in any way that we care, in any random way. However, there's something which is important, that in order to measure them or standardize them, scientists around the world should agree that our definition is both sensible and practical. Otherwise, it would create a problem. Now that we have set up a standard, for example, say for length, we must work out a procedure by which this length, whatever be it, should be expressed in a standard. So we must work out procedures by which length can be expressed in terms of the standard. Now, when we say that whatever be it, it can be measuring the radius of a hydrogen atom. It can be the wheelbase of a skateboard or somewhat the distance of a star. And these can be expressed in terms of the standard. Now, rulers, which are approximate our length standard, give us one such standard procedure for measuring the length. But remember, rulers cannot be used for measuring what is called the radius of an hydrogen atom or the distance of a very remote star. You cannot use ruler to do that. So, and also the problem is that there are so many physical quantities. For example, this length, mass, time, temperature, electric current, luminous intensity, force, and the list goes on and on and on. So the question rises that how we can measure those things, because these things have got a lot and they are not all independent. So what we do is that there are so many physical quantities, problem is to organize them. So what we do is that we do pick out, for example, by international agreement, a small number of physical quantities such as length and time and assign standards to them alone. So a small number of physical quantities assigned a standard to them alone. And we then define all the physical quantities in terms of these base quantities, or you can say base standards. Now, these base standards should have two characteristics. One is that it should be accessible, and always it should be invariable. Because if it varies, then it cannot be called as a base standard. For example, speed is defined in terms of the base quantities, length and time. So base standards must be both accessible and invariable, and that would make up things. Now, so from here, what we can say, for example, if we define the length standard as the distance between one's nose and the index finger of a person by an outstretched arm, we use an outstretched arm in order to measure the distance, we certainly have an accessible standard. But the problem is that it will vary from person to person. So the demand for precision, I would say in science and engineering, pushes us to the aim for invariability. Meaning what we want to establish base standard remains constant and unchanging over time. And also this ensures that everyone works with the same precise measurements, and the people around the world, there are no disagreements. And when we say that there are no disagreements, then what we try to say is a system, a standard, and that brings us to the next part of our video, International System of Units, SI, that we already know, but there is certain very fascinating and interesting history and revelations coming up into the next part of our video. Now, in 1971, in France, there was a general conference on weights and measures, and they picked out 7 quantities as base quantities, which forms the basis of what is called the International Standard System of Units, which is abbreviated as SI from its French name and is probably known as the metric system. Now, right on your screen, what you can see are the units of 3 base quantities: length, mass and time, that we use in the earlier few minutes in the earlier discussions of this video. And these units are defined as metric system, and they are defined on what is called a human scale. Now, what do I mean by human scale? For example, units like meters, length, seconds for time, and kilogram for mass are set to values that correspond to typical human experiences and activities, which makes easier to understand and apply in daily life. They are neither too large nor too small for common measurements, providing a convenient scale for human interaction with the physical world. Now, when we turn the pages of our history, we see that the SI unit for power, for example, is defined as watt. And this is defined as this. And you can read this, the last collection of units of symbol, as kilogram meter squared per second cube. I would again repeat, it is kilogram meter squared per second cube. Now, to express, I would say, very large and very small quantities, we often run into physics what are called scientific notations, as you can see, which employs power of 10. And scientific notation are used on computers, sometimes takes even a briefer look. For example, this one, 3.56 E9, where E actually stands for exponents of 10. Now, as a further convenience when detailing out certain things, you can see this is a kind of a table where you can see most of the factors, the prefix and symbol. But what is worthwhile to note is that, as you can see, that each prefix represents a certain power of 10, which can be used in a multiplication factor. How this power can be used for a multiplication factor? Let us look with a very simple example. And here you can see that attaching a prefix to an SI unit has the effect of multiplying by the associated factor. Thus we can express a particular electric power as this and a particular time interval as this, which is coming in terms of nanoseconds. So from here what we move is that, as here we can see that we are actually taking a diversion in terms of measuring them, and then we convert them multiplied by 10. What we come next are what is called changing units, and this is very important in terms of understanding physics and mathematics. So we often need to change the units in which physical quantities are expressed. We do so by a method which is called a chain link conversion. Now in this kind of a method, it is a method used to convert units of measurements by multiplying a quantity by a series of conversion factors. For example, if I want to take this one, 1 minute upon 60 seconds equals to 1 and 60 seconds upon 1 minute equals to 1. So the ratios 1 minute by 60 seconds and 60 seconds by 1 minute can be used as a conversion factor. But very important, this is not This can be taken as conversion factors. This one, 1 minute 60 seconds and 60 seconds by 1 minute. But what is important is that this is not the same as writing as this. Why? Because each number and its unit must be treated together. This is very important. Each number and its unit must be treated together. Why? Now we know that because multiplying any quantity by unity or by 1 leaves the quantity unchanged, we can introduce conversion factors wherever we find them useful. Now, for example, if we want to convert 2 minutes into seconds, we get into this. And if a conversion factor is introduced in a way that the unwanted units don't cancel out, we need to reverse the factor and try again. Here the minute has been cancelled out. But in case it is not, then you need to reverse the factor and try again. In conversion units, it follows the same algebraic rules as numbers and variables. Now, when we talk of changing of units, what comes the first thing is that how do we measure the length? And this length measurements also has a beautiful and a fascinating history and the further mathematics coming up into the next part of the video. Now, the newborn Republic of France around 1792 established a new system of weights and measures. And this is the cornerstone of what is called the meter. Now, meter, if you see, is defined to be 1/10,000,000th of the distance. And what is the distance? It is taken from North Pole to the equator. So here you can see the globe. It is from the North Pole to the equator, and it is defined by 1/10,000,000th of the distance, which is coming from North Pole to equator. Now later, due to practical reasons, this Earth standard was changed. It was abandoned, and meter came to be defined as the distance between two lines engraved near the ends of a platinum iridium bar. And the standard meter bar, as you can see right in the picture in front of your screen, which was kept at the International Bureau of Weights and Measures near Paris. So this is actually the standard meter that we talk in terms of measuring length, cloth, or anything when we talk of meter. This is the one. And it is defined by two fine lines near the ends of a platinum iridium bar. Now, accurate copies after this were sent to standard laboratories throughout the world. Now, these, I would say, secondary standards, or in 1960, I would say, there was a new standard which was required. So, secondary standard were used to produce from this bar, but eventually there was obviously a new standard, more precise, which was required, and in 1960 something new came up. So let us look into the next part of the video. So eventually a standard more precise than the distance between two fine lines was actually produced with a wavelength of light which was adopted. Specifically, the standard for the meter was redefined as 1650, I'm sorry I missed the 1650763.73 wavelengths of a particular orange-red light emitted by the atoms of krypton which has got a particular isotope or a type of krypton in a gas discharge tube that can be set up anywhere in the world. This awkward number of wavelengths was chosen so that the new standard would be close to the old meter bar. So this should be 1650, and I'm so sorry, I have missed on that. Now in 1983, however, the demand for a higher precision had reached such a point that even Krypton 86 standard could not meet it. And in that year, a bold step was taken. The meter was redefined as the distance traveled by light in a specific time. And in the words of the 17th General Conference on Weights and Measures, this is defined as to be this. The meter is the length of the path traveled by a light in a vacuum during an interval time of this. And that is why this time interval is chosen as the speed of light, which is this one. So the measurements of the speed of light had become extremely precise, and because it doesn't change, the speed of the light is invariant, so it made a sense to adopt the speed of light as a defined quantity and to redefine in terms of that iridium bar of, I would say, the meter. So having done with what is called length, the next thing which comes is this, time. Now, time had two aspects. For civil and scientific purpose, we want to know the time of the day so that we can order events in sequence. And another is that in scientific work, we want to know how long an event lasts. So thus, any time standard must be able to answer two questions. When did it happen and what is the duration? Now, any phenomena that repeats itself as a possible time standard. For example, this figure or the table actually shows some time intervals: lifetime of the proton, age of the universe, the Planck time, and so on. So what we do is that we take a quartz clock in which a quartz ring is made to vibrate continuously and can be calibrated against Earth's rotation. I mean to say via astronomical observations. However, there was a problem. The calibration cannot be carried out with accuracy called by for modern scientific and engineering technology. So what to do? So what happened is that in this National Institute of Standards and Technology, which is abbreviated as NIST in Boulder, Colorado, USA, to meet the need of a better standard time, physicists adopted what is called an atomic clocks. An atomic clock was set up at NIST, and the coordinate universal timer UTC was finally adopted. So the 13th General Conference on Weights and Measures, which was in 1967, adopted a standard second based on the atomic clock, and which is considered to be this. 1 second is the time taken by 91926317770 oscillations of the light of a specified wavelength emitted by a cesium-133 atom. Now this is the standard. I mean to say, as you can see earlier, what we did is that a quartz clock, but that was not good enough. The physicists adopted atomic clock in NIST, and this is taken with a cesium clock. If you're wondering what actually the cesium-133 atom does, this is here a quick idea. You can pause the video and just look into this. So this is a kind of an isotope of the element cesium, which is used by International System of Units, and in 1967 the second was officially defined as this. This means that the cesium-133 atoms are used in atomic clocks, which keep time by measuring these extremely regular oscillations, making them the most accurate timekeeping devices available. Now with time, what we come to next is that what is called a mass. And this figure which you can see, this is the standard SI standard of mass in a cylinder of platinum and iridium that is kept at the International Bureau of Weights and Measures near Paris. And this is basically is the SI standard of mass of platinum iridium, which we call is 1 kilogram. So this is actually the international agreement of the mass of how and what would be 1 kilogram, and then accurate copies have been sent across the world in other countries, and the masses of other bodies can be determined by balancing them. Now, if I ask you this question, how much a kilogram weigh, or I would put it in this way, that how actually is inside a 1 kilogram weight, then this is the answer. It contains 90% platinum, 10% iridium. It is preserved under 3 glass covers, and it lost about 50 micrograms in 129 years. And 50 micrograms is something the weight of your eyelash. And to let you know more is that kilogram is not the kilogram as it started, but it has been redefined in May 2019. And how it has been done, let us look into the next part of the video. So as you can see right on the on your screen, that this is actually been defined or redefined using Planck's constant. So what is the new measurement of kilogram? You can say this is this. And this is done actually by measuring the Planck's mass and using the equations E equals to h nu. So this has been redefined because it has undergone certain it has undergone certain kind of a loss. So this loss was again redefined. And this redefinition has been done, this was possible by what is called this one, which is called a Kibble instrument. We will look into that. But before that, this was the person Brian Peter Kibble, who actually invented what is called the Kibble balance. And this was improved version of the balance. And this was used in the current 2019 redefinition of the kilogram. And the Kibble balance actually looks something like this. So this is quite an old, but this is a highly precise instrument which came into use, and it plays a key role in the modern definition of the kilogram, which is now based on the Planck's constant rather than a physical object. So this Kibble balance, which is obviously a very complex instrument, now is redefining what is called a 1 kilogram, and this has been used using the Planck's constant and using the equation h equals to h nu. Now, this is all fine with very bigger sizes of physical matter. But what about how to calculate the mass of an atom? So remember, the masses of atoms can be compared with one another more precisely than they can be measured with standard kilogram. So for the reason, we have a second mass, and it is the carbon-12 atom, which is agreed by the international agreement. And this has been assigned as 12 atomic mass units, abbreviated as U, and the relation between the two units is this, with an uncertainty of plus minus 10 in the last 2 decimal places. So this scientists can with reasonable precision experimentally determine what is called the masses of other atoms related to the mass of carbon-12. So what we presently lack is a reliable means of extending that precision to more common units of mass such as kilogram that we are unable to do. So this plus minus 10 in the last 2 decimal places, however, this can be used as a standard to measure the masses of other atoms, taking the standard of carbon-12. We come to the last part of measurement, which is called density. Although in the upcoming videos I will be talking more about density, you can take this, which is defined by the Greek letter rho equals to mv, is the mass times v, and the density of water is a standard which is 1.00 gram and is often used as comparison. Fresh snow is about 10% of that density, and platinum is 2.45 grams per cubic centimeter. And remember that this, due to this high density of platinum, it is being used for various applications including jewelry, catalytic converters, and laboratory equipment. So we get a density of water, which is mass times volume. Then we get the fresh snow, 10% of that density, and we get platinum, which is 2.45 G per cm cube. So we take a pause on today's video where we have covered the fundamentals of the measurement, and then we will go up into the next part of the videos, which will cover up the real physics, the real mathematics of classical mechanics. So I would like to thank you for taking up your time and watching this video. If you have liked, please do subscribe to my channel by clicking on the bell icon and click on all to get all the notification from Physics for Students. You can also write to me for any further confusion at this email ID. You can also subscribe to my other channel, General Relativity Explained, and you can follow me on my Facebook, LinkedIn, Instagram, and Twitter account. Completing the first video on classical physics gives a kind of a motivation, and so keep a look on Physics for Students and stay tuned for further videos coming up on classical physics and various other topics on maths and physics. Till then, goodbye.